Okay, we're ready for problem 30. Second story problem. The demand D for a new roller ball pin is given by, so D is demand. I guess that the idea is how much something is wanted, how much people are wanting to buy it. You got this equation with the variable P, and P is the price in dollars. So they're trying to measure the demand, how much people will want something versus the price. It sort of makes sense. You would think the higher the price, the less people want it, and the lower the price, the more people would want it. So they asked a bunch of questions. You can see here dd, dp, which is a derivative. And so I think this is really like a first derivative kind of story problem. So let me write down this, what's called the demand function for this problem, and we can start working on it. So capital D equals 0.009 P cubed. I think with these decimals, the math is going to be sort of a pain. Everything's like a decimal. Minus 0.6 P squared plus 120P. First question, find the rate of change of quantity with respect to the price, dP. So when they write dP, they sort of give you a pretty big hint as to what they're looking for. It's like they're looking for the derivative of this demand function with respect to P. Looks pretty straightforward. So 0.009, you bring the 3 down, right? We know how to take derivatives now. Minus 0.62 P plus 120. I believe this is 0.027 P squared minus 1.2 P plus 120. I hope that's the answer. We will see. I think they just want the expression. .027 P squared, 0.027 P squared minus 1.2 P plus 120. Now the second part is, how many units will consumers want to buy when the price is 25 per unit? So basically you said, okay, so if the cost is 25, what will the demand be? So I'm going to plug in 25 into P into the original equation, all right? So I'm plugging 25 in for P into the original equation. So I'm really looking for original equation 0.00925 cubed minus 0.6 25 squared plus 120 times 25. Definitely a calculator kind of problem. 25 cubed times 0.009. 25 squared 20 times 25. Now, if I didn't mess up on my calculator, 2765.625. Don't know how many digits they want. Round to the nearest integer. So I would say 2766. Cross my fingers. Nice. Then they say C is find the rate of change at P25. The rate of change is the derivative. So now I'm going to plug in 25 into P into the derivative. I already plugged in 25 into the original demand function. Now I'm going to plug in 25. So originally, when you plug in 25 into the demand function, you're finding the actual demand when the price is 25. Now when you plug it into the derivative, you're finding how much is the demand changing when the price is 25. In other words, maybe is the demand going up or going down? If the demand is going down, then maybe that means you better quit raising the price. But if the demand is going up, that maybe means you can keep raising the price, because you want to sort of keep raising the price until the demand starts to decrease, and then you better stop. So let's do this. So I'm going to, in a sense, I can write it this way. Sometimes people write derivatives like this and they say, so I'm going to find the derivative when P is 25. So here's my derivative, 0.027 times 25 squared minus 1.2 times 25 plus 120. So 25 squared times 0.027 and 1.2 times 25. Whoops. 1.2 times 25, but you have to subtract that, plus 120. 106.875. So since it's a positive number, when the price is 25, the demand is still going up. That's probably a good sign for the company, if I did the math correctly. The number of consumers who want to buy will increase by, round to the nearest integer, 107, when the price is 25. Would you expect the GDP to be positive or negative? It's going to be positive. Well, I don't understand that. This must be some kind of interpretation. So anyways, I'm not sure what they're, but we did all the math. All right. Now, brand new sort of topic. This is called implicit differentiation. So let me do these problems, and hopefully you've already watched the video or learned how to do this. So this is 31. Let me write down this equation. 9xy plus 2 equals 0 and we want to know dy dx. The whole key to implicit differentiation is, the way I teach it is, the whole key is what you're taking the derivative with respect to. Here it's with respect to x, which it usually is. So anytime your variable is x, you just use our normal derivative rules. However, if the derivative is something different than x, you go ahead and apply the normal derivative rule, but then you have to tack on the extra dy dx. So once again, I'm not going to take the time to reteach that all now. Hopefully you've already learned it, and as we go through it, you'll see it. So normally what I do is, in a sense, really what you're doing is you're really taking the derivative. You could think of it as taking the derivative of both sides of the equation. So I'm going to take the derivative of 9xy. Of course, the 9 is just a coefficient, but x and y, that's two different variables. Remember the rule, when you take the derivative of two different sort of like functions, you have to do the product rule. So when I take the derivative with respect to x of this, I've got to use a product rule. The 9 comes out front. So the product rule says you write the first, and you take the derivative of the second. I'm going to take the derivative of y. So the first thing I do is I just think of y as a variable and apply my normal derivative rules. What happens when you take the derivative of a variable with no exponent? It's just 1. But because this variable is not x, because it's y, you take the derivative, and then you have to tack on the dy dx. So this is the first half of the product rule. The first derivative of y is 1 times dy dx, plus the second function times the derivative of x, which is also 1, but because this variable x is the same as what I'm taking derivative with respect to, I don't have to tack on anything else. Derivative of a constant is just 0. So if I multiply out the 9, I have 9x dy dx plus y equals 0. And now all I'm going to do is I'm going to solve this equation and get dy dx by itself. So 9x dy dx plus negative y. Divide both sides by 9x. dy dx is negative y over 9x. So negative y over 9x. Ah, did I mess up? I made a math there. You guys probably saw it. Oh, I forgot to distribute the 9. Yep, you probably saw it. So actually the 9s cancel out. I think it should be negative y over x. All right, got to be careful. Here's another one. X squared minus y equals 1. Solve for dy dx. So I think we're going to have a bunch of these in a row. Implicit differentiation problems. X squared minus y squared equals 1. And once again, they want to know dy dx. So once again, take the derivative of both sides with respect to x. So here we do these one term at a time. Derivative of x squared with respect to x is just our old-fashioned derivative 2x. minus derivative of y squared with respect to x, different variable. So you go and apply your derivative rules to y squared, which is 2y, but then you have to tack on the dy dx. Now the derivative of 1, which is a constant, is 0. So now we solve for dy dx. But you're going to have, we have 2x over 2y, x over y. I didn't make any mistakes this time. All right, a little bit different, little twist. Differentiate implicitly to find dy dx. So here's a function. We have to find dy dx. But they say then find the slope of the curve at the given point. Well, the slope of the curve, that's what dy dx is. Dy dx is the slope. So basically, we're going to find dy dx, and then we're going to plug in this point. We're going to plug in x equals 3 and y equals -7. So the answer is going to actually be a number. So let's write this down. Y squared minus x cubed equals 22. And we're going to look at the point 3, -7. Hopefully you understand what's going on. So here's a function, and we're going to find dy dx for this function. Dy dx is, in a sense, we've taught this the whole semester, dy dx, a derivative, is really the slope. So once we find the slope, then what they're saying is we'll go ahead and actually find the slope at this certain point. The slope is going to be some kind of equation that said, okay, let's actually go find the actual value, the number of the slope at this specific point. So the first step is we've got to solve for, or figure out dy dx, the derivative. So I'm going to take the derivative of both sides. On the left side, derivative of y squared, once in the variables are different, say 2y dy dx minus 3x squared equals 0. If I solve for dy dx, it's going to be 3x squared over 2y. So this is now the derivative, or you could say the slope of this equation. But now they're saying, all right, let's go look at a specific point and figure out what the slope is at that point. So they're saying go to 3, -7. So I could say dy dx at 3, -7. Which means here's my equation. I plug in 3 for x. And I plug in -7 for y. This is 927 over -14. Not real pretty, but unless I messed up, I think that might be the answer, hopefully. -27 over 14. Ha! I'm not totally surprised. Let me go back and look. Let's make sure I took the derivative correctly. 2y dy dx minus 3x squared equals 0. 3x squared over 2y. 927. I don't see where I messed up. Maybe you see it. Let me keep looking. Huh. Well, this is real life. Let me go back and work through it again, and you can watch me talk about it. Y cubed minus y squared minus, let's make sure I wrote down the, sometimes people write down the equation wrong. Y squared minus x cubed equals 22 at 3 negative 7. Write that here. Slope of both sides. This is 2y dy dx minus 3x squared equals 0. Now here I skipped a step, but if I didn't skip a step, I would have added 3x squared to both sides and then divide both sides by 2y. Dy dx equals 3x squared over 2y. Now I want to evaluate this at 3 negative 7, which means you plug in 3 for x. So I have 3 times x squared, 3 times 3 squared over 2y, 2 times negative 7. 3 squared is 9. 9 times 3 is 27 over negative 14. Now, I admit, this seems like a strange answer. Maybe they would make it a number. Maybe you can see what I'm doing wrong. Oh, you know what I think they want? They don't want, I think they want, which they're not very good about this. I think they probably want the actual equation. They don't make that clear at all. Let me try that. In other words, 3x squared divided by 2y. Wow. Very, very bad on their part. That is not clear at all. Now, when you plug in the points, negative 27/14. So I actually did it correctly, but I didn't quite understand what they were asking. And in my opinion, they were not very clear. Same kind of problem. Function and a point. So now we shouldn't mess up on this one. This is number 34. And it is x squared y squared equals 100. And we want to find the slope at the point 25. All right. Here's my original function. Take the derivative of both sides. Product rule here. I got two functions times each other. So the first times the derivative of the second, 2y dy dx. Then the second times the derivative of the first equals 0. solve for dy dx, I would subtract this 2xy squared divided by 2x squared y. If I cancel, those cancel. The x in the top left with x in the bottom. Negative y over x. Let's go ahead and evaluate it. At the point, it's like negative 5/2. All right, negative y over x. Then all right, not too bad. Here we're just finding, now they changed the variables, you notice, x and p cubed instead of x and y, to p dx. So the whole key is, what are we taking the derivative with respect to? This is still with respect to x, except instead of y, we have a p. So xp cubed equals 5. We want to find the p dx. Derivative of both sides of this. Got your product rule here. First times the derivative of the second. Now, since this variable is p, which is different than x, you have to tack on the p dx. Second half of the product rule, the second times the derivative of the first, which is just 1. Derivative of 5 is 0. If I solve for dp dx, it's like negative p cubed over 3xp squared. Cancel out the p's. Negative p over 3x. C, negative 3 over px. Oh, negative p over 3x. I didn't type in what I said. Negative p over 3x. All right. All right, assume that x is x to t and y equal to t. All right, so here's what we're doing now. This is preparing us what's called related rates. So I got this equation, y equals x cubed plus 2. And then they give us this other stuff. Find dy dt when x is 5. Here's what we're doing in this sense. Our original equation right here has got a y and an x. But then you see all this stuff with these dt's. What we're going to do is we're going to take the derivative of this equation with respect to t, almost like a brand new variable. In other words, the variable was not even in the original equation. So let me just, easiest way is probably to do it, and then you'll see that it's not that hard. So let me write down this equation, y equals x cubed plus 2. And they give us information, they say dx dt equals 4 when x is 5. Find dy dt when x equals 5. here's what we're going to do. You notice all these information we're given involves the variable t. So really we're taking, it's like all these derivatives are with respect to t. T is not even in my original equation. But that's okay, because what I'm going to do now is I'm going to take the derivative of both sides of this equation with respect to t. And in a few minutes, we're going to do problems where this t is going to represent time. And we're going to do what's called related rate problems, where we're looking at how things change over time. And we're going to look at how to solve those. So this is like a preparation for that. So the key is I've got two variables here, y and x. Neither of them are the same as what I'm taking the derivative with respect to. So using all my rules, on the left-hand side, the variable of y is just 1, but since the variables are different, I tack on the dy dt. Over here, I do these one at a time. The variable of x cubed, once again, x is different than t. I take the derivative, but then I have to tack on the dx dt. Derivative of 2 is just 0. Now there's a chance, it looks like they may want me to actually write down, once again, dy dt equals 3x squared times dx dt. Now I know eventually, you notice, they give me a value for x, 5. They give me a value for dx dt, 4. So I can plug in numbers into here and determine dy dt. But I wonder if they want me to actually give this equation first, like those last problems. So let's go and do the calculation just in case. So in other words, so here's the equation, and they were looking at a specific sort of situation where x is 5. So I plug in 5 for x, and the x dt is 4. So the dy dt at this specific situation is 25 times 4 is 100, 300. So dy dt when x is 5 is 300. But let's see how they want to put the answer. See, I'm going to guess here they want an actual expression. Let's see. dx dt. Nope. Maybe they want the actual number. Never know with these online programs. All right. Just thinking too much. All right. So now story problem, and this is called related rate. Related rate means you take some kind of equation and you include the time element. In other words, in the equation you have, it's changing with time. It's not the same. And we have to figure some things out. In other words, this one, a circle is growing. What's that mean? The circle is getting bigger all the time. Its radius increasing by 4 millimeters per second. Find the rate at which the area is changing at the moment when the radius is 13 millimeters. So they're saying you've got the circle and it's continually growing at a certain rate. And they want you to look at one point in time. The point in time is when the radius is 13. And they want to know how much the area is changing. What's the rate of the change of the area? So let me write down the information here. So it's a circle. I'm going to call it the radius rate, because that's what, when something's changing, it's called a rate. The radius is increasing by 4 millimeters. The radius rate equals 4 millimeters per second. And they want to know, in a sense, the rate of the change of the area, what I call the area rate, when the radius equals 13 millimeters. All right, now these problems are not hard. Now this one, the key is they don't give it to you. You have to know the equation for the area of a circle. Area of a circle is pi r squared. Remember, pi is just a number, 3.14. So with related rate problems, you have an equation or some kind of function, and you want to put it, in a sense, into the time mode, where this thing is not stable, it's not the same all the time, it's changing in time. And that's what they said. They said the circle is growing. So the way you take this and put it in the time mode, you take the derivative of both sides of the equation with respect to time. Now, pi is a number, but a and r are variables. So I'm taking the derivative of both sides with respect to time. On the left-hand side, a and t are different. Therefore, I take the derivative of a, which is just 1, but then I tack on the a dt. Now, pi is just a number. It comes out front. The derivative of r squared with respect to t is 2r dr dt. Now, let's look at what we have here. First of all, pi is just a number. The dt is the rate of change of the area. How fast or how slow is the area changing? So it's like area over time, in this case seconds. Here we have r, so it's just the radius at that point in time, at that instant. The r dt now is how is the radius changing with respect to time. So since the circle is growing, the area is changing constantly. That's what the ADT is. The radius is changing constantly. And here's the radius. So we're going to look at a specific point in time. They say when the radius is 13. So now it's like they're going to, it's like a freeze frame. The circle's growing, and they're going to freeze everything. When the radius is 13, they tell us the radius is changing, the rate of the radius changing or growing is 4 millimeters per second. And then they're saying, what is the rate of change of the area? So it's like you take this equation, you freeze it in time, and we freeze it when the radius is 13. They tell us the r dt is 4, find the a dt. So from up above, the a dt, I can write it 2 pi r dr dt. So I plug in 2 times pi, r is 13, the r dt is 4. Now, 4 times 13 is 40, 52, 104 pi. But I assume they're probably going to ask for a decimal answer. So 104 times pi, 326.726 square millimeters per second. So the radius determines the areas change at approximately, I think the units are millimeters per second. And how is it changing? Around there's thousands. I'm warning you now, this problem, don't plug in 3.14. You probably want to get the correct answer. You need to look for the little pi key on your calculator. Because to the thousands, 326.726. 326.726. So these are called related rate problems. Another one. A metal cube dissolves in acid such that the edge of the cube is decreased by this amount. How fast is the volume of the cube changing when the edge is 7.6? Same idea. Now we have a cube. The cube is melting, it's shrinking. And it's asking me some questions at a specific point in time. It's like we're going to freeze this cube as it's melting and answer some questions. So I'm going to write down this information. I'm not going to write down all the words because it's going to take time. So .3 millimeters per minute. And it's asking when the edge equals 7.6 millimeters. All right, what number is this? Number, I should write down the number so people can keep track. Number 38. All right. Got a cube. A cube is equal all four sides. We'll call the sides of the cube x. So the height is x, the length is x, the width is x. What is the volume of a cube? X cubed, right? But this cube is shrinking, it's melting, and it's doing equally. Each side's shrinking the same amount. Here's the equation for volume. That's what I call enter the time element. The way we do that is we take the derivative of both sides of this equation with respect to time. So you end up with dv dt equals 3x squared dx dt. So we've taken this equation for volume, and now we're looking at how is it changing with respect to time. Now I've got three things. I've got how is the volume changing, the rate of change of the volume, the rate of the change of the length of the side of the cube, and then the actual length of the side of the cube. So there's three sort of variables, three unknowns here. What they always do is they're going to give me two of these and ask me to find the third. So in a sense, this right here, this is how the side of the cube is changing. It said it's shrinking. So I really need to make this a negative because it's shrinking. Negative 0.3 millimeters per minute. So it's shrinking that amount every minute. And they're saying they want to know how the volume is changing exactly when the edge, the length of the edge is 7.6 meters. So once again, this cube is shrinking. We do a freeze frame. Boom. As soon as the length of the edge of the cube gets 7.6, we freeze it. And we're saying, this is how the side is shrinking. This is the length of the side. At that exact moment in time, how is the actual volume of the cube changing? So dv dt equals 3 times the length of the side, 7.6 meters squared. Dx dt, the rate that the length of the side is changing, negative 0.3. Well, I don't know if they're going to want the answer to be negative or not. I put the negative because that indicates it's getting smaller. Negative means something's getting smaller. We'll see in a minute. So 7.6 squared times 3 times 0.3, 51.984. It's going to be millimeters cubed per minute. And we may or may not have a negative here. It's according to probably how they do the wording of the problem. Now they say it's changing at a rate. Let me put in the negative and see. And they said the nearest integer. So it's actually, we'll put negative 52. We'll see if they like the negative. And they did. They do want the negative. All right, another one of these. Here, it's not a very straight problem. They just are calling this quantities A and B. But they give this equation that involves A and B, and they want you to enter the time element and then determine the ADT when A is 3 and the BDT equals 1. So really the same thing we've been doing. So this is 39. Let me write down this information. A to the 5th plus B to the 5th equals 275. dB dt equals 1. And they want to know dA dt equals what when A equals 3. I think it should be a pretty straightforward problem. So I'm going to take the derivative of both sides of this equation with respect to time. So it's 5a to the 4th times dA dt plus 5b to the 4th times dB dt equals 0. Now, if I want to solve for dA dt, it's going to be negative 5b to the 4th dB dt over 5a to the 4th. If you simplify it, the 5's cancel. I think it's negative b to the 4th dB dt over a to the 4th. Now the tricky thing is, I know dB dt, I know A is 3, I don't know B. Well, you know what you have to do? You plug in 3 for A into the original equation to figure out B. Little bit of a pain. So we better do that. So A is 3, so 3 to the 5th plus B to the 5th equals 275. So B to the 5th is 275 minus 3 to the 5th is 9, 27, 81, I think 243. So what is that? 32. So I think the 5th root Hope is 2. 5 times 4, 8. Very fortunate. B is 2. So now negative 2 to the 4th times dB dt, which is 1, over a to the 4th. Two to the 4th, 4, 8, 16, negative 16, over 3 to the 4th, 9, 27, 81. Negative 16 over 81, if I'm lucky. That was a lot of stuff going on. I don't think that reduces negative 16 over 81. All right. All right, I think there are a couple more of these. And then we'll be done with these sort of like related rate problems. Suppose that the price P in dollars and the number of sales of a certain item are, so P is the price, X is the number of sales. They give you an equation. If P and X are both functions of time, so things are changing. They're not the same, they're changing. And it's, the time is in days. And they say find the rate at which X is changing when X is 3, P is 6, and P dt. All right, so what we're gonna do is take this equation, convert it to time by taking the derivative of both sides with respect to t. Then I think we'll have everything we need. So we write down this information. This is number 40. The equation is 4p plus 4x plus 3px equals 90. So we want to know the rate at which x is changing. The x dt equals what? When x is 3, p is 6, and dp dt 1.1. Don't think it's going to be too difficult. Derivative of both sides of this equation with respect to time. 4 dp dt plus 4 dx dt. Now I'm going to have to use the product rule. The first times the derivative of the second plus the second times the derivative of the first. What I'm going to do, instead of solving this thing, let's just plug in all the numbers we have. In other words, we don't know this. We know everything else. We know dp dt is 1.1. 4 times 1.1. We know this is 4. 4 times dx dt, which is what we're solving for, plus 3 times 6 times dx dt, plus 3 times 3 dp dt is 1.1 equals 0. So 4.4, 3 times 6 is 18. This is 22 dx dt plus 9 times 9.9 equals 0. 22 dx dt. 9.9 plus 4.4 is 14.3. Move it over here. What are the chances I made a math error? Very possible. 14.3 divided by 22 negative 0.65. We'll cross our fingers. Sales per day, dxdt. All right. I think this is the last related rate problem. Volume of a cantaloupe. Now here it's nice, they give you the equation of the volume of like a sphere, a cantaloupe. The radius is growing at this rate at a time when the radius is this, how fast is volume? All right, this is what we've done all along. So now we have this volume of a sphere equation. So I don't think this is going to be that difficult. So 41, volume of a sphere, 4/3 pi r cubed. Maybe some of you remembered that. The radius is growing 0.6 centimeters per week. So we're measuring it per week. So the freeze frame, we're looking when the radius is 7.9 centimeters, and we want to know how the volume is changing. Going to take derivative, this equation with respect to time. Left side, dv dt. 4/3 pi, those are all just numbers or coefficients, they come out front. Derivative of r cubed, 3r squared dr dt. And we're solving for dv dt. I think we know all this stuff. 3's cancel out. 4 pi radius, 7.9 centimeters squared. The radius is growing at 0.6 centimeters per week. So grab your calculator, 7.9 squared times 0.6 times pi times 4, 470.56. Cubic centimeters per week. Oops, 0.56. Cross our fingers. Ah, I'll round to 1 decimal place. Yep, all right, so let's read the instructions. Looks like it should be 0.6. Didn't read the instructions. Very good. All right, that's related to rates. Looky there. Now we go to integrals. So we're going to stop now. And then we will start doing some problems with integrals.